All right, fantastic. Thank you very much. So yes, my name's Sam. I'm from the University of Queensland down in Australia. I am British, so do forgive me, but I am there for fun. And I'm here to give you a bit of I know we've been very snakebite heavy, but I want to make a bit of a case for scorpion envenomation and why we should care a bit more about it and why it matters around the world. So the aim of this study was to basically utilize high throughput electrophysiology to screen 12 different scorpion venoms for activity against 2 voltage-gated sodium channels, and thereafter compare the in vitro efficacy of 3 different antivenoms for that activity. In today's presentation, I'm going to start with a bit of kind of background about scorpions in Mexico and why they matter, then talk about some of the problems with the manufacture, and then also the efficacy testing of antivenom, and then go into kind of the body of what we actually found in our experiments. So to take a step back, scorpions in Mexico, there's about 300 species estimated across Mexico, so it's a very diverse country in terms of its scorpion populations. We see very heavy distribution of Centruroides. This is our most medically significant species, and then kind of spotty distribution of the other species as well. When we then come into actually looking at our envenomation data, one of the really good things about Mexico is that they have a very good system for recording envenomations. Anytime someone gets a sting and they report to a medical center, that is recorded, and we have a documentation of that over a long period of time. So we have a good long cycle. And what we see is in the southwestern region of Mexico, we have very high envenomations over the last year. So that's one state alone getting maybe up to 600,000 envenomations. It's a large number. And to put that into a bit of a global context, there's about 1.2 million globally. So Mexico as a whole, on a yearly basis, is getting 1/4 of the world's scorpion envenomations. Now, luckily, with that, we see a very low fatality rate. We're estimated to be about 30 deaths per year is what was recorded. But one of the main considerations of those deaths is that 90% of those are in children under the age of 10. So it's a very difficult disease, difficult issue for children of young ages. But what we can generally see from that data is we're getting very high reporting of envenomation, but low fatality. So what that tells us is that people seeking medical care are likely having high morbidity associated with their envenomation syndrome. That's why they're seeking medical care. They may not be dying, but they're not having a very good time when they're being stung by these scorpions. And to go a bit more into what actual scorpionism looks like, we have cumulative symptoms that start from mild to moderate to severe. And all of these kind of look like sum up to be a very neurotoxic envenomation syndrome. We start with universally, all scorpion venoms will cause pain. It's the universal fact. Then we can move into more moderate symptoms, which can typically in Mexico be symptoms such as tachycardia and convulsions, particularly in children convulsions. They are very vulnerable to it. It can cause issues such as breaking bones. And then moving into severe symptoms such as our pulmonary edema, paralysis, and ventricular arrhythmia, which can become those life-threatening envenomation symptoms. So how do we actually deal with this? Well, the answer is, of course, antivenom. Now, scorpion antivenom is made much the same as snake antivenom. We rely primarily on equine immunization of our venoms to generate our antibody products, which we then typically cleave into forming our FAB2 fragments. So obviously, a lot of work is being done to kind of remove the animal dependency in this sort of antivenom sphere. But when we test our scorpion antivenom, we still rely on the gold standard lethality assay in mice. So we give different concentrations of our venom with our antivenom, then we inject it into mice 24 hours later, and we look to see if the mice are dead. But why are we doing that for scorpions? Scorpions don't kill humans. So if we're having different effects in humans than we are seeing in mice, there's a bit of a mismatch between what we're observing in our envenomations and what we're actually trying to achieve in our efficacy testing. Another issue that I just wanted to come and look at quickly is the fact that antivenom obviously relies upon our immunizing mixtures. And so there are 3 main antivenoms in Mexico. We have Inoscorpi, Bermix, and Alacramin. Bermix and Alacramin are much older. They've been on the market since like the late 1990s. Then Inoscorpi is a much newer antivenom coming into the market now. We have a range of venoms that make up these. One of the main issues they actually have is they're not using pure venom all the time to make these antivenoms. Sometimes they're using the macerations of the telsin, so they just snip the telsin off, crush it up, and that's what gets injected for the immunizing mixture, which is obviously you get a lot of byproducts from doing that. And so one of the main goals of this study was to try and look at differences between these antivenoms in terms of their efficacy for our neurotoxins within these venoms. So to circle back to the actual aim of this study, we're trying to use high throughput electrophysiology. And what that meant for me was using QPatch, which is from Sophian Biosciences. It's a platform for wholesale patch clamp electrophysiology, and it allows us to use up to 16 channel biochips. There are now newer ones, but at the time, 16 channel was very impressive. And what we can do is we kind of reduce the risk of error associated with manual patch clamp It also reduces manual handling error because there's automated pipetting, which generates a low failure rate. We can use cells that we have given, we've transfected with our ion channels that we're interested in, and it also gives us quite broad cell compatibility. And finally, that we can use a bit more of a direct competition assay design to test our venoms against our antivenoms. I'll show you what that looks a bit more like in a second. Just to give you a bit of context of what it looks like when we're looking at our ion channel activity. In blue is our normal ion channel. We see baseline, we see depolarization, we see the opening of the ion channels, which goes to a reduction in our current and then return to normal. So we see that's a normal activity. If we introduce our venom, we might expect to see some changes to this because it might block or interfere with our channel activity. So what does the direct competition model look like? So what we have here in this picture down here is we have what our cell looks like in the well. We have two electrodes clamping it in the middle, and we have basically two solutions on either side. We have a high salt concentration at the top and a low concentration at the bottom. And what we're able to do is measure the current across the whole cell as our ions are moving through that cell, and the changes in the current as those ion channels are opening and closing allow us to effectively tell what's happening in that cell. And in this assay, what we're able to do is preload our solution around those cells with our antivenom, and then introduce our venom immediately. Rather than doing some pre-incubation, we have our venom directly acting against our antivenom in that solution. And well, it also enables us to test that there's no activity between the antivenom and the cells of any form. And so it gives us a more direct competition between the two. For this study, I selected, as I've said, two voltage-gated sodium channels. That's NAV 1.4 and NAV 1.5. We heard a little bit about NAV 1.5 from Glenn yesterday. It's a cardiac ion channel. It has an important role in how our heart functions. And then NAV 1.4 is a predominantly skeletal muscle ion channel. And we're looking at these two because we want to look back to those symptoms of the morbidity symptoms we observed earlier, where we've got tachycardia, we've got convulsions, paralysis. Some of these might be tied to these particular ion channels because we know they're neurotoxic venoms. We want to try and see if our antivenoms are effectively neutralizing the neurotoxins that target these channels in particular. And we're doing this in vitro rather than doing it in vivo. These are all the different scorpions that we ended up using for this project. You might also see there's a little odd one out. We have a Brazilian species of Titius cerulatus, whereas the rest are all Mexican scorpions of different degrees of medical importance and different localities around the country. The reason we have the Titius in there is because we wanted to try and see if there was any cross-reactivity in our antivenom in terms of similarities between the neurotoxins targeting these ion channels and whether or not they could be inhibited. So what did we actually observe when we started to introduce our venoms to our ion channels? Well, across the board, we saw very little activity against our NAV 1.5 channel. We didn't really see any inhibition of activity. In fact, when we tested these at the same concentrations down to 0.4 microgram per mil, where we saw a strong effect on NAV 1.4, we saw nothing on NAV 1.5. We had to bump it up to more than 100 times that to get any activity on NAV 1.5, so we suspect that it's not particularly relevant in the same degree that the NAV 1.4 toxins were. And what we can see here is we saw that, so if it just to give you a little look, so we see our normal and our NAV 1.4 activity, there's very little difference between our two ion channels. Then if we look at our NAV 1.4, we see our saline is nice opening channel, whereas that's completely inhibited by our NAV 1.4, by our scorpion venoms against that activity. This was not universal across all of our venoms, however. We saw that there was quite a bit of variation in terms of potency at the same concentration. And then again, we saw just very little NAV 1.5 activity, which is interesting given the kind of severity of cardiac symptoms that can be associated with the Centruroides envenomation. When we then actually took that activity and decided we want to start looking at how the antivenom interacts with it, we found that pretty much across the board, our antivenom was effective in terms of neutralizing that inhibition of our channel activity. However, we found that there wasn't necessarily the same effectiveness or efficacy of that antivenom inhibition between each of those antivenoms. We found differences between them. And interestingly, if we look at our two most potent venoms in terms of their NAV 1.4 inhibition, which is the only channel that we continue to test on, as we saw so little activity on NAV 1.5, we can see that actually our inner scorpion antivenom, so that's might be a little bit hard with these colors, I won't lie. So on the far left, we have venom, then inner scorpion, then Burmex, then alacramin in each of these figures. So we found that our inner scorpion antivenom was significantly different from one of our other antivenoms in terms of its neutralization capacity. Then we saw that again in Centruroides limpidus, where we have our Burmex antivenom, which is significantly different from both other venoms, from both other antivenoms for Centruroides limpidus. And then we observed that exact same activity in Centruroides sculpturatus, where we see Burmex is significantly poorer at neutralizing that inhibition of channel activity. And if we look at the immunizing mixtures for these antivenoms, we actually see that in terms of Centruroides elegans, where we had our poorest activity for inoscopy, that is within the immunizing mixture, which is a confusing kind of outcome there. And Centruroides limpidus, all three of those antivenoms contain that venom. And then Centruroides sculpturatus, inoscopy is the only one that does contain that. But we're still seeing from alacramin some neutralization of that activity. When we then look at a couple of other venoms, so this is just a snapshot of all of them. I didn't want to go through absolutely everything, just in the interest of time. With Centruroides noxious, we see very much the same activity again, where Burmex is our poorest performing antivenom of the three, and we see strong inhibition of that, or strong neutralization of that channel inhibition from both inoscopy and alacramin. Interestingly, we did observe neutralization of our channel activity for Titius cerulatus. It was a bit of a poorer inhibitor of the NaV1.4 channel, but we did see some cross-reactivity in our antivenom against that activity. And obviously, that's not within the immunizing mixture of any of those antivenoms. And then Centruroides noxious is included in the immunizing mixture of all three of those antivenoms. So some of the kind of key takeaways that I want to kind of say from this assay, and it kind of ties in, parts of it tie into the discussion that we had yesterday at lunch, just after lunch. Our crude venom activity was greater upon NaV1.4 than NaV1.5. And this was not necessarily equivalent across all species that we tested. Our antivenom cross-reactivity was observed for Titius cerulatus. That has implications for whether or not we could potentially use antivenom across different borders. As if you may or may not know that Titius cerulatus is a scorpion that has parthenogenetic capabilities in Brazil. It's having a massive spread throughout the country right now. It's basically able to live in just about any conditions, and particularly loves homes. And so Brazil is having quite an issue with the surge in Titius cerulatus species causing envenomings throughout Brazil. I hope to make a bit of an argument for the fact that this is an in vitro assay capable of looking at antivenom efficacy for individual toxins of against a channel of interest. And in our case, because we have a very neurotoxic envenomation, we know that the ion channels are very important in our envenomation syndrome. It's not necessarily the same case for snakes, but I know across scorpions, it is always an ion channel reaction that we're interested in. We know that we can effectively test whether our antivenoms can neutralize that activity. Obviously, it goes without saying that my studies, therefore, are not truly replaceable because we have one ion channel, but they act upon a multitude of ion channels simultaneously. But the reliance upon that can be reduced by targeted use where we have known channels of interest associated with some of our clinical symptoms. And then in terms of future directions, I think there is a pressing need, and I think it does tie into yesterday, there is obviously a pressing need to move antivenom efficacy beyond lethality and look at some of the more important morbidity symptoms associated with that envenomation syndrome, and that therefore this needs to come from a policy level down. We need to promote, and the importance of this kind of assay in adopting non-animal based models to test our antivenom efficacy is, in my opinion, quite important. As we say, we need to move towards reducing our reliance on animals, and I think this could be a good opportunity to, as a stepping stone for a technique to do that. I'd just like to say thank you to Lee for coming along, members of the Fry, King, and Veta Labs, and of course my supervisors and all of the co-authors, particularly Dr. Jonathan Chow, who was basically taught me everything. So appreciation to him. Oh.